Welcome to this talk. I'm very happy to be here. I want to thank the team, the Code Blue conference team, for having me. So thank you. So today I'm going to talk to you about passive fingerprinting of HTTP to clients. Before we begin, though, I want to run a small poll. You can all go to www.poll.si and use that code, just so we know how many of you actually understand or know how HTTP2, how the protocol actually works. So take a moment to do this. I'm going to put this in the back so we see the results. You have it here. Come on. Be active. Okay, it's going in the direction I actually expected. We'll give it another 15 seconds, maybe. It takes time to log into the URL. Yeah, so the point of the survey is actually to explain why I'm going to spend somewhere around half of the presentation actually talking and explaining what HTTP2 is, how it works, all the inner workings, so that you'll have good understanding of what it is that I'm talking about when I'm talking about the fingerprinting. So that's very important. So thank you for taking the poll. I'm going to leave it open for you. We can check it out later on, but I think it made the point. So a little bit about me. My name is Segal. I'm from Israel. I work at Akamai as the director of threat research. I have been doing web application security for close to actually more than 20 years now. I'm an officer of the Web Application Security Consortium. How many people know what WASC is? OWASP, maybe? Good. So I'm also an OWASP Israel board member. I filed about 20 patents in the field of application security, mainly around static analysis, dynamic analysis, integrated application security testing, and other things. Some of the research articles that I wrote were pretty famous, although I think I'm most famous in Israel for being a part of the band PITS. Yeah. Feel free to download their music. I will make a few bucks out of that. So what are we going to cover today? First, we're going to talk about a few words about Akamai, actually one slide. I'm not trying to push or to sell or to pitch anything. I don't think it's even relevant. I just want to show you what kind of data Akamai has access to. And we'll talk about that in a second, which makes this, I think, research more accurate and more appealing for the reader. Then we'll do a little bit of an overview on HTTP2. Actually, that will take us through the, most of the presentation. We'll talk about that. Then we'll talk about passive client fingerprinting, what it is, why do people use it, and how do we do that today. And then we'll talk about how do we do passive fingerprinting using HTTP2 client attributes and features. We'll talk about the use cases for this fingerprinting. And then we'll wrap up with a quick overview of the threat landscape. So a few words about Akamai. Again, this is not a sales pitch. So Akamai is the world's leading CDN platform. It's been around since the 90s. I'm pretty sure that most of you heard about Akamai. And if not, you're using Akamai probably now with your computers. We have installed and we have deployed over 200, now it's actually 250,000 edge servers across the entire web. We're located in 3,300 different locations around the globe, over 1,200 cities in 129 countries, and such networks. And our latest peak traffic reached 60 terabits per second. Just to give you a bit of proportions about what kind of traffic we're talking about here. The data that we see at Akamai is amazing. Actually, I keep telling people that this is how I pitch for people who I want to hire for my team, for the research team. Once they see the amount of data that we actually have, it's pretty much a closed deal for them. So we see 3 trillion web hits every day from 1 billion unique IPs every quarter. That's basically everything out there. We collect about 13 trillion log lines every single day. That's about 260 terabytes of compressed logs. And we see in a normal day anywhere between 15 to 30% of all actually internet traffic, not web traffic. So that's pretty amazing. The things we do with this data, we actually collect it into a platform called Cloud Security Intelligence, which feeds a lot of our products, our intelligence. We make our products smarter. This is just one example. You can actually go to this URL and see it has 2 views. One is a map and the other one is a spinning globe, where it actually shows you live attacks, web application layer attacks, of course. When we came to research HTTP2, we went to first see how much are people actually using HTTP2 on the internet. Now, many of you probably think that it's not in existence, right? Raise your hand if you think that you're not using HTTP. Okay, so my mistake. So in a normal day, we see about 13,200 hosts or applications using HTTP2 today. Over 600,000 different unique user agents from 25.6 million IPs, doing about 413 million logins every day. And this all went into the research that you're now seeing, and over 1 trillion hits. So roughly saying, and this is only from our security data platform, we estimate that the amount of HTTP traffic on the web today is about 10%. This is a Twitter take a photo moment if you want. I believe it's actually a bit more. Again, this is only based on our security big data platform, not on the entire Akamai platform. So let's go over HTTP. So HTTP is actually a new protocol that was introduced in 2015. It was based on a previous protocol that Google experimented with and pushed to Chrome and to their servers called SPDY, S-P-D-Y. So it was published in 25. There are actually 2 RFCs if you're interested in reading RFCs. Some people like to do that. The first one is for the actual protocol. The second one is for what is called HPAC. That's the header compression that is used inside HTTP. And we'll get to talk about that a little bit later. I think the most important purpose of HTTP, or the reason it came into being, was to improve performance. There are a lot of issues, performance issues, inherent to HTTP 1.1 and 1.0, obviously, and we're going to talk about them now. So HTTP 1.1 didn't really handle concurrency very well. If you open a browser and you go into a page and you see that the page is loading a lot of different images and scripts, at some point you see that it's stuck, the page is stuck. The reason is that it's using a lot of different TCP connections up until the browser's limit. Some browsers limit it to 10 TCP connections and so forth. So there's no real concurrency other than these TCP connections. But on each TCP connection, you can only send a request and wait for a response. You can't do things simultaneously. The other problem with HTTP is compression. Now, there is compression in the form of gzip encoding, for example, through the content accept encoding header. However, the headers themselves, which make a nice chunk out of the HTTP request, are going back and forth between the client and the server. So things like the cookie, the user agent, the connection header. There's so many different pieces of information that are flowing back and forth between the client and the server, and there's really no reason to keep stating them other than, in the beginning of the session. So for example, the user agent shouldn't really change. I can send it in the beginning and then forget about it. So that wasn't really handled in HTTP 1. The other and the last part was actually that the server is passive. So I am a client, I come to the server, I ask for a page or a resource, I get the resource back. I ask for another resource, I get the resource back. The server is never allowed to send me stuff or data or resources, even if it knows that I'm about to send them. So for example, if you're going into the root directory into index.html, and that page is known to be loading CSS files, JavaScript files, and so forth, why not send them over already in a proactive way rather than wait for the client to ask for them? So the server was passive in HTTP 1. So here we see HTTP 2. Now let's see the differences. So concurrency is actually handled in a different way. In HTTP 2, you only use one TCP connection. That's it. The browser is only allowed to open one TCP connection, one port. You remember, everything is very simple. And on that TCP connection, the browser is allowed to open what is called concurrent streams. We'll talk about the streams in a second. So everything is concurrent or virtually concurrent inside this single TCP connection. Compression is handled through what I mentioned earlier called HPACK. So headers are packed, zipped in a sort of a way using Huffman codes as well, and then transported only in the headers frame. I'll actually talk about that in a moment. And that's it. We forget about the headers for the rest of the session. So it's very efficient. And a very cool new feature for performance, server push, was introduced. So the server is allowed to forecast when a client will need some resources, and will push those resources through a push frame down to the client, where it will wait on the TCP stack or on the browser stacks on the browser side. And when the browser wants to fetch these resources, they will be fetched from the cache. So that is super fast, super efficient. You can see, by the way, a very nice demonstration of this at the Akamai website. There's http2.akamai.com. I can show you a demo later on. So how do we handle concurrency when we have only one single TCP connection? So we have the client, obviously, and we have the server. They form a TCP connection between the two. And then they define what are called streams. So streams are virtual streams on top of the data, basically. You can open as many streams as you want. Browsers define how many streams, or clients and server can define in the beginning of the session how many streams they support. And the streams are numbered from 0 to n. Usually the client uses the odd numbers, and the server uses the even numbers. I might be mistaken. If you catch this mistake, I apologize. So let's take a look at one of the streams. Again, this is an example of one of the many streams. Could be thousands of streams that are running concurrently. So the stream is an independent bidirectional sequence of frames. We'll talk about what frames are, that are exchanged between the two parties. So here's an example of a frame going back and a frame going from the client to the server. A frame doesn't need to live alone. It can have multiple frames in one message, for example. These two frames traveling together, like a headers and the body. That's basically it. They can run concurrently. Nobody has to wait for each other. Now let's talk about some of the elements that I mentioned. So a connection is that single TCP connection, the transport layer connection between the two endpoints. The stream is a bidirectional flow of frames inside an HTTP connection. A frame is actually the smallest unit that exists in HTTP 2. So there are different types of frames. We'll look at that in a second. We actually use that in the fingerprinting. And the frame is, consists of a header part and then the actual payload. And if it's hard to, comprehend, I'll show you a graphical example of it. And a message that's not something that actually exists. It's not mentioned in the RFC. A message is basically what you know from HTTP 1, where I send a GET request or a POST request, and I get a response. So a request or response, that's pretty much a message. So how does the frame look like? In the beginning, we have the length of the frame, so an integer telling us what is the length of the frame that we are about to receive. the type of the frame, which is an 8-bit number, the different flags, a reserved bit, because you always have to reserve 1 bit when you write a new protocol, and a stream identifier, which basically says to which stream this frame belongs to. You remember, this whole thing is virtual on top of TCP. And then the payload. The payload can be 0, so no payload, like in a headers frame, or it could be, a body of post or whatever you want to send, or a response for that matter. So let's take a look at a real headers frame for a simple HTTP request. Bless you. We have the length, which I didn't bother to calculate. I apologize. And then we have the type. So this is a headers frame, so the type is 1. I'll show you the different types in a second. The different flags, again, we have multiple flags here. We have the end headers, which is 4 hexa, the end stream, which is 1 hexa, and the priority flag, which is 20 hexa. If you add them together, I hope you get to 25, or else I came out like an idiot. The reserved bit, the stream identifier, in our case 73, and some padding, in this case 0. The exclusivity bit, which we're going to talk about in a second, the stream dependency, so on what stream does this stream depends on? We'll talk about that in a moment. The weight of the stream, again, we'll talk about that in a moment. And then the actual, I hope you're comfortable with this. This looks pretty similar to what you're used to. However, don't get used to it because the protocol itself is binary, and I'll get to that, so it doesn't really look like this, okay? It's all packed and made of bits. So what frame types? We just saw one, headers. Let's see what frame types exist. So we have data frame. So let's say I asked for a request, I got a response. The response will come back. The chunk of response will be back inside the data frame. We have the headers. We have a priority frame, a reset frame, settings. I'm not going to read all of them. We'll get back to a few of those in a second when we start fingerprinting clients. So how do you inspect HTTP traffic? And this is the tricky part. And I believe the sad part. So in HTTP 1, everything was very simple. You open net, like I use netcat or burp or whatever, right? You open netcat, you type netcat, whatever, host, port, hit enter, write get, host, send enter, and you get the response. That doesn't work anymore. And we'll get to that. So your best odds for debugging HTTP traffic in HTTP 2, first is to use debug logs on the web servers. These are debug logs from, I believe, Nginx. Pretty cool logs to read. On the client side, forget about burp. I'll get back to that in a moment. But if you open Chrome, if you launch Chrome, and you go to Chrome, semicolon, //net internals, you actually get a very cool debugger. I'm not sure if a lot of people know about it, but it allows you to debug connections both in HTTP 2 as well as Quick, which maybe will be my next year's presentation if I get accepted. And you can see the live sessions, and you can see the headers, and you can see the flags, and you can see everything I'm talking about in this presentation. So let's take a look at how a session is initialized. We'll try to do it a bit quickly. So we start a session. This is from the client side, and the client defines the host, whether or not the request is proxied. The protocol is H2. By the way, the HTTP 2 is always transported over TLS, over SSL, encrypted traffic. And so the clients usually define that they want or declare that they want to talk HTTP 2 using the server, the SNI, the server name, the protocol negotiation extension. I apologize for that. So that's one of the ways for a client to actually say to the server that they want to talk HTTP 2 when they start a TLS connection. And then we see the client sending a few settings. That's the settings frame. So they're defining all sorts of numbers there. I'm not going to go into that. We'll talk about some of them in a moment. And then they send the window update, and that's basically the part of the headers that you know. And then if we look at the actual request, the first header frame that is being sent, this looks pretty similar to what you know the method, the host or the authority, the scheme, the path, user agent, and headers, etc. And then the server will reply with something very similar to what we know from HTTP2 or HTTP1, the status code, the headers, and if there's some body to the response, they will send another frame, a data frame containing the data. So that was simple, right? Okay, so a few things to keep in mind. So what I'm showing you is textual. However, the protocol itself is binary, so don't try to use Netcat, don't try to use Burp, don't try to use any of those tools that you're used to them. It's also implemented, and it's not mandated, by the way, by the RFC. However, all current implementations are only supporting HTTP2 over TLS. So there's no clear text HTTP2 traffic on the web today. Yay. Most intercepting proxies, like I said, I'm a big fan of Burp. Couldn't use it for debugging HTTP2 traffic. I think only Charles proxy supports HTTP2 from the ones I saw, and MITM, man-in-the-middle proxy, a command line intercepting proxy tool, also supports HTTP2, albeit it doesn't show you the, the different flags and everything on the lower level that I was talking about, but you can intercept the traffic and work with it. If you're a command line person, go ahead. This is how it looks like, by the way, if you try to sniff the traffic. If you do want to sniff the traffic with Wireshark, you need to first make sure that Wireshark is configured to decrypt TLS traffic. You can point it to the secret log files if you use Chrome and decrypt the traffic. It also has like one of those view plugins for HTTP2, so it's pretty cool. However, if you just sniff the traffic, this is how it looks like. So a few words about passive client fingerprinting. I'm pretty sure that most of you have used tools like P0F, or I call it POF, or other passive client fingerprinting, like Nmap does some passive, mostly active, by the way. But so why do we need the passive client fingerprinting? So this is the passive collection of attributes that clients and servers exchange during a conversation to try and understand what is the other party, what kind of client it is. We can fingerprint usually software clients, not end users. We're not interested in tracking, or I'm not interested in tracking users, maybe others are. But we're trying to understand who's speaking to us, what kind of web server, what kind of client, what kind of browser, that kind of fingerprinting. As far as I know, there are 3 layers to do passive fingerprinting. You have the transport layer, or in English, TCP passive fingerprinting. That's a very cool technique, by the way. Session layer, TLS fingerprinting, again, very powerful. And application layer, so you can look at HTTP, for example, and look at the order of the HTTP headers and sort of deduce which kind of client is talking to you, even if they spoof the user agent. So what can you learn from passive client fingerprinting? You can learn about the type of operating system and the version even, and we'll talk about that in a moment. With passive TCP fingerprinting, if you're talking to a Unix-based machine, you can actually deduce pretty accurately the uptime. So when was the last time that the system rebooted? That's very cool to see that it's the same person over and over again. And of course, the client type, the software client type. What kind of browser, what kind of version, what kind of command line client is being used, and so forth. So let's take a step back and get back to the types of the different frames. Now, when we came to research passive fingerprinting of HTTP, we knew that we needed to find things that are consistent per client type, because I need something that will be consistent everywhere that client goes to. And obviously to be unique, to have some or enough entropy so that I will be able to separate between the different clients. So out of these frames, the only ones that we could use for the fingerprinting were these ones. The headers frame, the priority frame, the settings frame, and the window update. Fear not, I'm going to explain in very low level now how they are being used. So let's start with the settings frame. You actually saw some of it earlier. The setting frame is basically an exchange of configuration settings between the client and the server in the beginning of the TCP, of the HTTP 2 session. I apologize. This is a must. It's mandatory. You cannot start an HTTP 2 session without defining the most basic settings. How does it look like? Here's an example from one of the browsers. Again, settings have different types. You can see in the RFC, type 1 means the header table size that the client supports. Type 3 is the maximum concurrent streams. You remember we talked about the streams earlier. And then number 4 is the initial window size. We'll get to that in a second. And then there's the value. So each client hopefully will have a different value, so we will be able to fingerprint them. Because if everybody will have the exact same values, not very good for us. So we came up with this very trivial and obvious fingerprint format. So the setting, or the setting ID, and then colon, and then the number, or the value. And then you can have, you need at least one, right? But you can have as many as the settings that exist in theory. A word about the entropy of the settings. It's actually pretty cool. You can see here, and I guess, yeah, in English. There, 2 Android mobile devices. Both of them are running Android. Both of them are running Firefox, even though it's different versions. But the settings themselves are pretty unique. You can see this one, and this is something else. This is what we were hoping for when we started the research, so we were very happy. The next thing we looked at was the window update frame. Now, HTTP 2 performs flow control inside the HTTP 2 protocol. And so you need a way to update the window size. So the flow control operates at 2 levels. There's the individual stream, so you can define, or the client can define the window, the maximum window size for a specific stream or for the entire connection. And the RFC defines that the default window size is 65K. However, no client actually uses 65K. Each of them sets their own value, which is very good for us for fingerprinting. You see that once the connection starts, the client can send or modify the initial window size using the window update frame. There's a frame for that, a dedicated frame that you can send. How does it look like? Very simple. Again, I'm decrypting the binary crap. So the window update frame has some stuff attached to it for stream ID 0. Sorry for these folks here. So stream ID 0, and then how much do we want to increment the size of the window? Pretty simple. So how do we add that to the fingerprint that I talked about earlier? Very simple. We use a pipe character, and we add the value after the settings. So we have the settings first, pipe, the Windows update. If the window update is not sent, nobody updates the window update, we just write 0, 0 instead. Priority frame. So different streams can set different priorities. So for example, if you have the main index page being transported over the first stream, you may want other streams to be dependent on that main thing. So you want to give priority and dependency to the streams. So you want to start with the index HTML, make sure that this gets the highest network traffic priority, and then the other streams that are responsible for the auxiliary files, for the CSS files, the fonts, the JavaScript, and whatever. That's a very cool feature, by the way, that sadly, at the moment, I believe only Firefox actually uses. However, it exists. So we set the stream dependency and the priority, like I said. We assign weights, so who is more important than who. And it's defined in the beginning of the connection, which is good for us for fingerprinting again. So each frame includes 3 fields. I show them. the weight, the dependency, and the exclusivity bit, which usually is 0. So this is actually the Firefox settings in the beginning, the priority frame settings. You see the different, it's actually pretty sophisticated, but that's the default. When Firefox opens an HTTP connection, that's how it sets the priorities for the different 5 frames in the beginning. And this is how we encode it for the fingerprint. So you have the stream ID, you have the exclusivity bit, the dependency stream, the stream it is dependent on, and then the weight. I want to stop and summarize for a moment. So this is where, up until now, what we have is basically this. This is 3 examples, by the way, from real clients. And then the fingerprint that we have up until now contains the settings in the beginning, delimited by pipe, the Windows update value, which in this case wasn't sent, so it's 0, and then the priority and the weights. I hope this is clear. So, are we there yet? Can we fingerprint the clients at this point? Obviously, you can. It's not as accurate as it could be. So we discovered one last interesting twist to the story, which are the pseudo headers. If you remember, earlier I talked about, I showed a few examples. They had some semicolons. You'll see it in a second. So HTTP 1 had the request line. I hope that everybody's know that. You had the method, the path, the HTTP version, and then CRLF, and then you continue. That's the request line. That doesn't exist in HTTP 2. Instead, we use what's called a pseudo header field, which is prefixed with colon. So again, I hope you're all familiar with this simple example. This is a get slash with HTTP1 to example.com. How would that look like with pseudo headers in HTTP 2? Like this. So you have the method. There's no request line. There's the method with the semicolon, the colon, sorry, the path, authority, that's basically host, and the scheme. And then the rest of the headers, which don't include the colon in the beginning. So, 4 headers, how much combinations can you actually get from this, right? How much entropy can you actually get from 4 header names? We all know combinatorics. However, for some reason, every single client that we checked had a complete different order, which is ridiculous because it's so simple. Just pick one and go with the rest of the crowd, but they wanted to be special. So each of the clients actually put the headers in a completely different order, which is very cool if you're trying to fingerprint. That's some more bits of entropy. It's going to be hard to look, to see, but you will have to believe me that we looked at the Chrome's source code inside their Git, and they actually put the headers inside an object or class called headers in a certain header order, which matched the header order that we saw on the wire. However, it's probably a hash, so why would it keep the order? So if you look at the class itself, they actually state that this class provides a key value map that they use in Speedy, and it actually preserves the insertion order. So that explains the order that we saw and how it looks on the wire. Firefox, the same thing. So each of them actually hard-coded the header order. So where are we with the fingerprint format? So we have the settings in the beginning, pipe, the Windows update, pipe, the priority part, I'm going to go to that side, the priority part, and then the pseudo headers encoded as a single character. So method, authority, the path, and the scheme. Let's take a look at a few examples, real world examples from clients. This is a Chrome 58 on my MacBook Air. I updated since then. And you can see the fingerprint here. This is Edge browser, Microsoft Edge browser on Windows. Again, different fingerprint. This is Firefox 53, again installed on my Mac. Again, different fingerprint, so this is going well. OKHTTP, that's a library, very popular with Java developers. Again, unique fingerprint. And curl, again, unique fingerprint. And this goes on and on. I couldn't obviously fit all of these. However, each client has a very unique and very distinct fingerprint that you can passively use for doing stuff. We'll talk about what stuff is in a second. I apologize. Okay. Are we with time? Good. So, what can we do with passive HTTP to fingerprinting? The first thing we do is we can detect clients that spoof the user agent, and that's very popular. A lot of attack tools, security tools, scrapers, bots, they spoof their header. If they spoof their, the user agent header. If we know how the user agent header, how the HTTP2 fingerprint looks like, we can check this inconsistency and figure out that somebody's trying to lie to us. That's very easy. You see somebody claiming to be Chrome, the header order looks like OKHTTP. It's obviously a developer or some security pen tester that actually is spoofing the user agent. You can detect attack tools and bots. We actually created a directory at Akamai of all the known attack tools. I'll talk about some of them in a moment. Most of them don't support HTTP2. We'll get to that. You can do positive enforcement. So for example, let's say your organization or your company exposes a mobile API for the mobile application. It's very easy to whitelist the type of HTTP2 fingerprint that you expect because you wrote to the client, you know exactly how it looks like. Anything else will be blacklisted, so positive enforcement of web client types. And my favorite, detecting anonymous proxies, anonymous VPNs, Tor, whatever you want. This is very easy if you do statistical analysis on the traffic. For us at Akamai, it's very easy. You observe traffic over time from a certain client. If you see a single, for example, TCP fingerprint, multiple TLS fingerprints, multiple HTTP2 fingerprints, you add it all up, you figure out that it's actually a proxy. So, let's take a break from the fingerprinting and talk a little bit about HTTP2 threat landscape. So what kind of attacks is Akamai seeing from those trillions of HTTP requests that I mentioned earlier? And the answer is nothing. No attacks whatsoever. And we're going to spend a moment talking about why that is the case now. Now, it's not completely true. There are some attacks that we're seeing. However, the numbers weren't that interesting, so I didn't want to come out like an ass showing low numbers. So why is this happening? If you take a look at the different attack tools, and I'm pretty sure that most of you, there's a Japanese name for burp. If you look at these tools, and this is a list of tools that I usually use, my team uses, I'm pretty sure that some of you use. By the way, how many of you used AppScan in the past? IBM AppScan? At least one hand? Yay, I wrote it. So none of these tools actually support HTTP2. No support. I called my friend who wrote burp, and I asked him, when can we expect support for HTTP2? I really need it. We're trying to write this paper on fingerprinting, and we have no tools. And he said, not on the roadmap right now. We have other priorities. And this is a common answer from all of these tool writers. I'm very surprised to see SQL Map not supporting HTTP2. If you think about it for a second, if your website today only speaks HTTP2, you get an extra layer of security for free. Right? Nobody can attack you. Let's say you're vulnerable to SQL injection and nobody can use SQL Map. Good luck trying to do all that, blind SQL injection with the keyboard. So, why don't these tools support HTTP 2? So, like everything, the first problem is money. There's no real incentive, no real financial incentive, no real incentive at all for supporting HTTP 2, because at the moment, all the servers support, have back compatibility to HTTP 1. So you can always downgrade, or you can even not start an HTTP 2 session. So why bother with developing these tools to support HTTP 2 if the servers anyway support HTTP 1, right? The other problem is the support of libraries. So there are more than a few libraries that support HTTP 2. However, they are not the normal, common, prevalent libraries that we see for people who write tools that use HTTP. So liburl in Python, which I personally use, lib or Perl, www, etc. They don't support HTTP 2. You have to use new libraries, which means that you have to refactor your code to support these libraries, or else you have to do this on the wire. That's actually one of the interview projects that I give to new people that come to work for my team. I let them actually code an HTTP client from scratch, binary in Python. So we did see, and some folks, I think last year or 2 years ago almost, published some findings about bugs in HTTP 2 implementations, weaknesses, where servers didn't handle compression and stream management, sorry, and other things. However, in order to exploit these, you don't really need these tools. You don't need SQL map, you don't need burp, and so forth. So there are tools for that, but you can't use them to debug traffic. And with that, I want to do a quick recap. So we talked about Akamai in the beginning, but we talked about how HTTP 2 works. I hope that right now, if we do the poll again, more people will actually be able to answer that they understand HTTP 2. It's very simple. Like I said, launch Chrome, launch Chrome Net Internals, and just look at it. It's very simple. We talked about the differences between HTTP 1 and HTTP 2. And we talked a little bit about what is passive fingerprinting. And we also discussed how you do passive fingerprinting with HTTP 2. And then, sadly, we talked about the lack of attack landscape for HTTP 2. Hopefully, by next year, I'll have some, I don't know if to say better or worse news for you about this. And that's it. Thank you.